Have you ever looked up at the night sky and wondered how the stars' light reaches us, even though they're millions of light years away? Light. It travels faster than anything we know. But have you ever asked, why? Why does light have a speed limit? And more importantly, why can't it go faster? What's stopping it? Tonight, we'll take a quiet journey through space and time. We'll gently explore the deepest rules of the universe, rules that even light must follow. And in the process, we might just discover something about the rhythm of reality itself. But before we begin, if you're someone who enjoys drifting into sleep while thinking about beautiful, mind-opening mysteries, then you're in the right place. This channel is made for you. So, if you haven't already, take a calm moment and subscribe. Not to follow trends, but to follow curiosity, gently, one night at a time. Now, let's begin. Light is one of the few things we never really stop to question, because it's always been there. From the moment we open our eyes in the morning to the final sliver of moonlight slipping through the window at night, light just is. But what is it? Really? Some say it's a wave. Some say it's a particle. Strangely, both are right. And also, neither are completely right. Let's slow things down. Imagine you're standing by a quiet lake. You pick up a small stone and drop it into the water. You watch the ripples, calm, wide, smooth, spread outward, softly disturbing the surface. That's how light behaves, like a ripple, a wave. It doesn't need anything to carry it, unlike sound, which needs air. Light moves through the vacuum of space, all by itself. But here's the strange part. Light also behaves like it's made of tiny particles. They're called photons, little packets of energy, like tiny messengers traveling at impossible speed. When you switch on a lamp, millions upon millions of these photons are released instantly, flying out in every direction. Some bounce off your book, some hit the wall, and a few lucky ones land softly in your eyes. And in that moment, you see. But here's where it gets truly mysterious. These photons, these tiny pieces of light, they don't have mass. They are completely weightless, like thought or memory. They exist, they travel, they interact, but they never rest. Nothing in the universe can travel at the speed of light unless it has no mass. And light is the only thing we know that lives in this strange in-between space. Not quite matter, not quite energy, but something beautifully both. Now let's take a step deeper, because this is where things get almost spiritual. Light doesn't just bounce around like marbles in a jar. It can bend, it can split, it can interfere with itself. It can disappear from one place and reappear somewhere else, as if it knew you were watching. In the famous double-slit experiment, scientists shined light through two narrow slits. You'd expect to see two straight lines of light appear on the wall behind them. But that's not what happened. Instead, light created interference patterns, bright and dark bands as if waves were overlapping, like the ripples on our lake earlier. But then, scientists tried something strange. They placed a detector just to watch which slit the photon went through, and everything changed. The interference disappeared. The wave became a particle. Just by watching, the light changed its behavior, as if it knew, as if it responded to being seen. Now pause. Let that settle in your mind for a moment. Light behaves differently depending on whether or not you're observing it. It's not just mysterious, It's almost poetic. Light has always played with duality. It travels both as a wave and as a particle. It can light up galaxies, or sneak through the tiniest crack in your curtain. It warms your skin and powers your thoughts. Because yes, your brain, it only works because of light. Tiny signals of electricity, which are just energetic particles, flow through your neurons, guiding memory, movement, emotion. In a way, we are built from light, and we are moved by light. But how fast does it move? We'll get to that soon. But first, let's sit with this one truth. Light is not just something you can see. It's the very language the universe uses to communicate. From the light that left a star 1 billion years ago to the glow of your phone screen right now, photons have traveled unthinkable distances, crossed empty stretches of black vacuum just to reach your eyes and deliver their quiet message. I am here, I have arrived, and yet, as real as it feels, you never actually see the world in real time. Even light takes time to travel. Every image you see is a tiny delay, a moment that has already passed. You're always looking into the past, even if it's just a few billionths of a second. Isn't that beautiful? That even something so fast still obeys the rules of time. It doesn't cheat. It doesn't rush. It simply travels at its exact speed. Always the same. That constant speed, 299,792,458 meters per second, is not just a number. It's a boundary, a universal truth, a cosmic heartbeat. And yet, why that speed? Why not faster? Why can't we ever go beyond it? Why does light have a limit? If light is so magical, why does the universe stop it from doing more? That's the next part of our journey. But for now, just breathe. Feel the mystery of this strange traveler, the one that paints the skies, carries our thoughts, and fuels every moment of life. Light is not just fast, it's fundamental. It's not just what helps us see, it's what helps us be. Next up, we'll explore why the universe doesn't let anything move faster than light. And what happens if you try? Light is fast, unimaginably fast. So fast that it circles the Earth 7 times in a single second. But for most of human history, we didn't even know it had a speed, let alone a limit. There was a time when people believed light traveled instantaneously, that the moment you lit a flame, its glow touched the world all at once. No delay, no travel, just light. And honestly, it made sense. After all, when you turn on a lamp, the room lights up instantly. You never see it arriving, it's just there. But there were a few curious minds who didn't accept the obvious. They wondered, what if light does have a speed? What if it's just so fast that we can't measure it yet? Let's go back to the 1600s, to the days of telescopes and stargazers, to a time when science still wore robes and carried lanterns. One of the first people to seriously ask this question was Galileo Galilei. He believed light might have a speed, and he wanted to test it. He and an assistant stood on 2 distant hilltops with covered lanterns. The idea was simple. Galileo would uncover his lantern, and the moment his assistant saw it, he'd uncover his lantern in response. Galileo would then measure how long the light took to come back. But there was one problem. Human reaction time was far slower than the light. The delay between the lanterns was less about speed and more about how long it took for someone to realize they'd seen light. So Galileo concluded that if light had a speed, it was far too fast for him to measure. And for a while, the mystery stayed quiet. But about 50 years later, a Danish astronomer named Ole Romer changed everything, and he wasn't even trying to measure light. He was just watching the moons of Jupiter. You see, Jupiter's largest moon, Io, moves like clockwork. It orbits Jupiter and disappears behind it at regular intervals. But Romer noticed something odd. Sometimes, Io seemed to disappear later than expected, and other times, earlier. He was puzzled. How could a moon be off schedule? And then it hit him. It wasn't the moon that was changing, it was us. When Earth moved closer to Jupiter in its orbit, light from Io had less distance to travel, so it arrived faster. When Earth moved away, the light took longer. The moon wasn't late. Its light just had more space to cross. And just like that, Romer became the first person in history to estimate that light has a finite speed. He didn't get the exact number, but he was the first to prove that light takes time. It was a quiet revolution. Now fast forward to the 1800s, and the name Armand Fizeau. He designed a much more precise experiment. No moons, no telescopes, just clever physics and a spinning wheel. He shined a beam of light through a rotating gear toward a mirror placed kilometers away. The light would bounce back and ideally pass through the same gap. But if the wheel spun fast enough, the light would come back to find the next tooth in the way and be blocked. By adjusting the wheel's speed and measuring the distance, Fizeau was able to calculate how fast the light must be moving to make that return trip in the blink of an eye. His result? About 313,000 kilometers per second. Not perfect, but very, very close. Later, another physicist named Léon Foucault refined it even further, using mirrors instead of gears, and measuring the delay in the beam's return. And with every experiment, humanity got closer and closer to the true speed of light. Eventually, in 1983, we stopped measuring it altogether because science reached a turning point. We realized something profound. The speed of light isn't just fast. It's not just impressive. It's fundamental. It's not just a speed. It's the speed, the ultimate constant of the universe. So instead of trying to measure how fast light goes, we redefined our units of measurement around it. Today, the meter is defined as the distance light travels in 1,299,792,458 of a second. Let that sink in. We no longer ask light to fit into our definitions. We bend our definitions around light because it's that important. Every time you measure distance, you're in a way measuring light's journey. But despite all of this precision, one mystery still remains. Why is light this fast? Why that number? Why can't it go any faster or any slower? We can measure it. We can observe it. We can depend on it, but we still don't fully understand it. It's like a secret the universe is keeping, a secret it lets us use, but never fully explain. Light moves how it moves, and everything else follows, even time. So the next time you flip a switch, or look at the stars, or watch the morning sun climb over your window, remember that what reaches your eyes isn't just brightness. It's history. It's distance. It's a miracle wrapped in motion. And somewhere, far beyond our senses, light continues its endless run, never stopping, never slowing. But why? Why can't anything go faster? And what would happen if it did? That is where we go next. In the early 1900s, The world was changing. Trains were faster, cities were louder, and the sky was beginning to fill with machines. But beneath the noise, a quiet revolution was brewing. A young man, with wild hair and tired eyes, working in a patent office in Switzerland, was staring at light and asking a question no one had asked quite like this before. What happens when you try to chase a beam of light? His name was Albert Einstein. He was just 26, unknown, unemployed as a physicist, and yet, in the silence of that office, he changed the universe. Because while most scientists were trying to measure light, Einstein was trying to understand what light was trying to tell us. He imagined, if you could run next to a beam of light, if you were fast enough to keep up with it, what would you see? Would the light freeze? Would it stop moving? Would time itself pause? What he discovered was stranger than anyone expected. Let's slow this down. Imagine you're in a car, driving down a quiet highway at night. You turn on your headlights. The beams stretch out ahead of you, as always. Now imagine you start speeding up, faster, faster still, until you're traveling at nearly the speed of light. What would happen to your headlights? Would the beams stretch out, slower and slower, because you're catching up to it? Logic says yes, but the universe says no. No matter how fast you go, even if you're nearly keeping up with light, it will always move away from you at the same speed. 299,792,458 meters per second. It doesn't matter whether you're standing still or racing through space at impossible speed. Light's speed never changes. This was the heart of Einstein's special theory of relativity. He proposed that the speed of light is a universal constant, unchanging, untouchable, unbreakable. But to make that true, something else had to give. And what gave way was time. Time, something we all take for granted. We think it moves forward, second by second, like drops from a leaky faucet. But Einstein realized something revolutionary. Time is not fixed. Time is relative. If you move faster, your experience of time slows down compared to someone who's still. Let that sink in. If you and your twin are the same age, and you take a journey across the galaxy at near light speed, when you return, your twin will have aged more than you. Not because of magic, not because of tricks, but because you traveled closer to the universal speed limit, and time itself changed its rhythm for you. This is not science fiction, it's science fact. We've tested it. Astronauts on the International Space Station experience tiny amounts of time dilation. Their clocks move just a little slower than ours on Earth. Atomic clocks flown in airplanes return slightly behind their ground-based twins. It's real, and it all flows from one truth. Nothing, absolutely nothing, can go faster than light. And as you approach that speed, time slows down, mass increases, and space itself begins to warp. But why can't anything go faster than light? Why did Einstein call it the cosmic speed limit? Let's imagine you're pushing a shopping cart. At first, it's easy. You give it a gentle push. It moves. Push harder. It moves faster. Now imagine that cart is moving near light speed. To go just a little faster, you have to push a lot harder. And the faster it goes, the heavier it becomes. Not just metaphorically, but literally. As something approaches light speed, its mass increases. And to keep accelerating it, you'd need more and more energy. Until eventually, to reach the speed of light, you'd need infinite energy. Which, as far as we know, the universe does not allow. So light, being massless, can move at the speed of light. But anything with mass, no matter how small, can only get close, never equal, never beyond. This isn't just about motion, it's about causality, the order of cause and effect. If someone could go faster than light, they could outrun information. They could receive a message before it was sent, arrive before they left, undo time. The universe, it seems, won't allow such chaos. So it draws a line in the fabric of reality, a boundary, a limit, and that limit is light. Einstein's insight didn't just rewrite physics, it redefined how we see everything. Space is not separate from time. It is space-time, a connected, stretchable fabric. Time is not the same for everyone. It bends, based on motion and gravity, and nothing can move faster than light, because if it did, reality itself would unravel. All of this, from a young man wondering what it would be like to chase a beam of light. He didn't need a lab or a telescope, just imagination and the courage to question the obvious. And thanks to him, we now know that light is not just fast. It's not just beautiful. It is fundamental. It is the ruler against which the universe measures everything else. So the next time you see a sunset, or stare at the stars, or watch headlights cut through fog, remember, you are witnessing the limit of motion, the edge of time, the fastest anything can go, and the silent law that holds the cosmos together. But now that we know light's limit, what happens if we try to go beyond it? Is there any way to cheat the system? Any cosmic loophole? Let's find out in the next part of our journey. So far, we've discovered that light is the ultimate speed limit of the universe. Einstein taught us that nothing with mass can ever reach, let alone surpass, that speed. But what if, just for a moment, we let go of the rules? What if you could outrun light? Let's take a slow, quiet step into imagination. Not because it's scientifically possible, but because it's curious. And curiosity, after all, is what makes the mind dance, even when the body rests. So tonight, let's imagine a ship. Not just any ship, but one designed to chase light. It hums quietly, no engines, no flames, just a silent glow beneath its surface. And you are its only passenger. At first, you're drifting, peacefully coasting through the black velvet of space. Stars stretch out in every direction. Still, silent, endless. You look ahead, and in the far distance, a beam of light pulses outward, a cosmic flash moving at the speed of light itself. You set your course. You accelerate, slowly at first, then faster still. You feel no wind, no pressure, but the stars begin to stretch, not visually, not like lines in a movie, but time itself begins to behave differently. Your clock ticks slower, your thoughts slow down. You move closer, closer, closer to light speed. And now, you reach it. You're flying at the exact same speed as light. And strangely, something feels off. Because you can no longer see the light ahead of you. You're traveling alongside it, but you cannot catch it. Not truly. It's like chasing your own shadow at the speed of thought. But now, let's go one step further. Let's say, somehow, you go faster. Just 1 meter per second beyond the speed of light. A tiny edge, a small cheat in the cosmic rules. What happens next is not what you'd expect. Suddenly, time around you begins to fracture. You pass a planet and see events happening in reverse. Rivers flow backward. Leaves unfall from trees. Voices rewind like broken recordings. A rocket launches from the sky and lands calmly back on its launch pad. You're moving faster than information itself, which means you are seeing the past before the present even arrives. In your frame of reference, cause and effect break apart. You could arrive at a destination before the light carrying your image ever gets there. You could see a star explode, and then, moments later, watch it go back to burning peacefully as if the explosion never happened. You're not just faster than light. You're faster than knowledge, faster than truth. And now, the questions begin to spiral. Could you send a message before you send it? Could you receive news of an event before it takes place? Could you undo choices, avoid accidents, relive time? But here's the problem. As you outrun light, you also outrun understanding. Reality begins to break. The rules that govern physics, time, space, energy, they stop cooperating. Why? Because light is how the universe communicates with itself. It's the messenger of motion, of time, of awareness. By surpassing it, you tear through the very threads that connect moments to each other. You're no longer traveling forward. You're unraveling the path behind you. And soon, you're no longer sure which way time is flowing. Are you watching history or predicting the future? Are you aging or rewinding? Your ship feels the same, but your memories don't. One moment you're passing stars. The next, those same stars are unpassing you. You feel a chill, not physical, but cosmic. A sense that you have gone too far. Back in the world of real science, this thought experiment, as wild as it seems, has been studied in theoretical physics. And every time we try to break light's limit, we run into paradoxes. We violate causality. The basic idea that something must happen before something else reacts to it. Break that rule, and nothing makes sense anymore. You could prevent your own decisions, erase your own existence, create loops of time that never resolve. Physicists call these scenarios causal paradoxes, and the universe doesn't seem to allow them. It's as if light's speed isn't just about motion, it's about protecting order, because without that order, reality becomes unwatchable. Like a story being told backwards, out of sync, with no beginning and no end. So while the idea of going faster than light feels magical, it also feels wrong. Not in a moral sense, but in a structural sense. It's like trying to divide by zero, or trying to stand still in a falling elevator. There's no reference, no meaning, just chaos. So maybe the universe has a reason. Maybe the speed of light is not a limit, but a guideline. A law written into the code of reality, not to restrain us, but to keep the story moving forward. So now, we return to our ship. You slow down, the stars return to stillness. Time realigns. Causality snaps back into place like elastic. You're moving beneath the speed of light again, and suddenly, the universe makes sense. Not because it's simple, but because it has rhythm and light. Light is the metronome. So, what if you could outrun light? Perhaps it's better that you can't, because in doing so, you'd lose the story of time, the beauty of cause and effect, the heartbeat of reality. And sometimes, the most loving thing a universe can do is say no. No, you cannot go faster. No, you cannot reverse. Just move forward, slowly, consciously, one beam at a time. In the next chapter, we'll return to the quiet question. Why does light even have a speed at all? Why that number? Why not more or less? let's explore what makes this cosmic speed so perfectly balanced. Speed is exhilarating. Even here on Earth, in cars, in planes, on trains, we love the feeling of motion. The faster we go, the more we feel alive. But in the universe, speed has a cost. Not in money, not in fuel, but in something more fundamental: mass. And tonight, we'll explore a strange but beautiful idea: that the faster you go, the heavier you become. Not metaphorically, but literally. Let's begin gently. Imagine you're pushing a swing. At first, it's easy, a soft nudge, and the swing glides forward. Push again, and it swings higher. Now imagine trying to push a giant boulder. A single shove barely moves it. It resists. The swing was light. The boulder is heavy. Mass in physics is resistance to motion. The more mass something has, the harder it is to make it move, or to stop it once it's moving. So far, so simple. But now, let's imagine you're in space, far from planets, stars, or gravity. Just you and a spaceship. You give the ship a little burst of energy. It begins to move. You fire the engines again, more energy, and it goes faster. You keep repeating this. Energy in, speed out. But then, something strange happens. Each time you push harder, you gain less and less speed. It's like the universe is resisting. But why? Einstein gave us the answer. As your speed increases, so does your mass. Not the kind of mass you can see or weigh on a scale, but the mass the universe feels when it tries to accelerate you. This is called relativistic mass, and it's part of the way reality defends its most sacred law. Nothing with mass can reach the speed of light, because if it did, its mass would become infinite. And to move something with infinite mass, you'd need infinite energy, which the universe does not give. Let's slow that down again. You, sitting calmly in your ship, might feel weightless. But the faster you go, the more space-time itself sees you as heavy. It's not that you're gaining physical matter. It's that you're becoming more difficult to push, more resistant, more anchored to the speed you already have. It's like trying to run through thickening syrup. Each step takes more effort than the last. Eventually, you hit a wall. Not a physical wall, but a wall of energy. You could fire your engines forever, but you'd never reach the speed of light. You'd get close, incredibly close, but never quite there. Let's use an example that's real. At CERN in Switzerland, scientists use a machine called the Large Hadron Collider, a ring of magnets nearly 27 kilometers long, to accelerate tiny particles called protons. They push them faster and faster and faster until they're traveling at 99.9999991% the speed of light. At that speed, these tiny protons are moving through space at almost light speed, but they still don't reach it. Why? Because to accelerate them even a tiny bit more, it takes a massive amount of energy. And every time you give them energy, they don't just go faster, they become heavier. So much so that they weigh thousands of times more than they do at rest. Not on a scale, but in how hard they are to accelerate. Speed becomes expensive, and eventually, it becomes impossible. But this isn't just a barrier, it's also a gift, because this limit creates stability. If particles could move faster than light, they could become infinitely massive, collide with infinite force, and collapse everything around them. Galaxies could fall apart. Atoms could tear themselves open. The universe could burn itself down. But instead, the universe whispers, "No, that's far enough." And here's something even more beautiful. Because of this cost of speed, time itself begins to change. We've talked about time dilation, how clocks tick slower as you move faster. But did you know that even light itself obeys this principle in a unique way? A photon, a particle of light, travels at the speed of light, which means that, for a photon, no time passes at all. From its perspective, it leaves a star, crosses millions of light years, and reaches your eye instantly. Not in 10,000 years, not in seconds, but in zero time. Because when you move at the speed of light, time stops. You are everywhere and nowhere, in motion and still, part of all things and separate from them. But again, only massless things can reach this realm. Photons, glimpses of energy, the messengers of the universe, and everything else. Everything made of atoms, bones, thoughts, and dreams is bound to stay just below that limit. Maybe that's part of the plan, because this limitation gives rise to time, to change, to cause and effect, to stories. If we could all travel at light speed, there would be no moments, no sequences, just an eternal flash. But because we can't, life unfolds in beautiful rhythm, 1 second, then the next. So yes, speed has a cost, and that cost is weight, resistance, energy. But maybe that's what keeps us grounded, what gives meaning to every step forward. We're not meant to flash instantly from one point to another. We're meant to travel, to move through time, to feel the journey, and the universe makes sure we do. In the next chapter, we'll step into the strange world of light in the quantum realm, where photons play by entirely different rules, and reality itself seems to shimmer with uncertainty. So stay close, because the mystery is just beginning. By now, we've seen how light bends time, resists speed, and defines the very structure of reality. But in the tiny microscopic world, where particles are no bigger than dust floating in moonlight, light becomes something even more strange, even more dreamlike. Welcome to the quantum world. Here, light isn't just fast, it's unpredictable. Let's begin with something that still confuses even the most brilliant scientists: the double-slit experiment. Imagine a wall with 2 narrow slits. Behind it, a screen that can detect light. Now shine a gentle beam of light at the slits. You'd expect to see 2 bright lines where the light passed through, simple, like throwing pebbles through 2 gates. But that's not what you see. Instead, you get an interference pattern, a ripple of light and dark bands, as if the light interfered with itself, like waves, overlapping, canceling, and combining. So, is light a wave? Seems like it, but here's where it gets weirder. Try sending 1 photon at a time, tiny particles, 1 by 1. Still, you get the same wave-like pattern, as if each photon went through both slits at once, as if it interfered with itself, like it was in 2 places at the same time. But then, try to observe which slit the photon goes through. Place a tiny detector, and instantly, the pattern disappears. Light behaves like a particle again. Just 2 lines, no interference. It's as if light doesn't like being watched, as if the act of observing it changes what it is. Wave becomes particle. Mystery becomes certainty. This is the heart of the quantum mystery. Light is both a wave and a particle, not one or the other, but both, until you look. And once you do, it chooses. But why? No one really knows. Some say it's randomness. Others say it's deeper, that consciousness may play a role. But in truth, the quantum world remains gently unknowable. Even Einstein was troubled by this. He once said, "God does not play dice with the universe." But quantum physics replies, maybe. He does. So what is light, really? A particle? A wave? A probability? A mystery? Maybe it's all of them. And maybe light's true form depends not just on where it is, but on whether we're watching. Next, we'll ask, why does the universe need this limit at all? What purpose does the speed of light really serve? Let's explore that in the next part. By now, we've asked the big questions. What is light? Why is it so fast? And why can't we ever catch it? But tonight, let's ask something even deeper, not just why the speed of light exists, but why the universe needs it. Why place a cosmic limit at all? Imagine a universe without rules, where signals could arrive before they're sent, where causes don't always lead to effects, where moments happen out of order, or not at all. It wouldn't be peaceful. It wouldn't even be chaotic. It would be meaningless, because meaning needs structure, and structure needs boundaries. The speed of light isn't just a number. It's a boundary between what's possible and what's paradox. A line drawn into the very fabric of space-time. And this line keeps the universe coherent. It ensures that stars light up before their glow reaches us. Events happen in sequence, not scrambled like dreams. Messages travel at predictable speeds. So communication can exist at all. Without this limit, you could receive a signal from a star before it even formed. You could turn on a flashlight and see its light before you flipped the switch. Everything would collapse into contradiction. So maybe this limit is the universe's way of keeping itself sane, a way of saying there is order, there is rhythm, there is balance, and within that balance, life can unfold, thought can emerge, time can move forward, moment by moment, like a story, one sentence, then the next. So, the next time you look up at the stars, remember, they are bound by the same law. They shine and they wait patiently for their light to reach you. Because even across the galaxy, the universe honors its own pace. It doesn't rush. It doesn't skip ahead. It just moves with quiet perfection, one beam of light at a time. Next, we gently begin to wrap up our journey. What does this mean for us? If light has limits, do we? Let's reflect. In the final part, we often take it for granted that light moves at the speed it does. Exactly 299,792,458 meters per second. Not a little more, not a little less. But have you ever wondered? What if it didn't? What if the speed of light was just a bit slower or faster? Would anything change? The answer is, everything would. Let's imagine for a moment that light moved slower, maybe only half its current speed. What would that mean? Well, it would take longer for sunlight to reach Earth. Instead of 8 minutes, maybe it would take 16. Stars would twinkle with more delay. Galaxies would seem even more distant. But it's not just what we see, it's what we are. Because the speed of light isn't just about light. It's woven into the very equations that describe our universe. Einstein's famous equation, E equals mc squared, that c is the speed of light. And if you change it, you change the relationship between mass and energy. A slower speed of light would mean stars might not burn as they do. Fusion reactions could be weaker. atoms might behave differently, and life as we know it might not exist. The universe would be dimmer, colder, perhaps quieter. Now flip the thought. What if light were faster? At first, it sounds exciting. Messages would arrive instantly. Stars would shine almost immediately. But the laws of physics would twist. Time dilation would become extreme. Distances would lose meaning. And mass-energy relationships would warp. Even small particles could unleash massive energy. A single atom might behave like a tiny sun. In such a universe, everything would happen too fast. Stars would burn out quickly. Galaxies might not hold together. There would be no time for stories, no slow unfolding, no room for reflection. Everything would flash by and vanish. So maybe there's a reason light is just fast enough, not too quick to burn out creation, not too slow to freeze time, but balanced, perfectly tuned to allow stars to live, planets to cool, atoms to bond, and beings, like us, to ask these quiet questions. In our final part, we'll return home. What does light teach us about time, about limits, and about ourselves? Let's reflect together. Thank you for being here. If this journey touched your curiosity or your heart, consider subscribing. There's so much more to explore. Together, good night, twilight.